Okay, it's time to start. Thank you very much to be here. And my name is Antonella Ferrara. I'm the chair of the editorial board of UCA, and so I'm very honored to be here, actually, in my role of chair of the semi-plenary section. And it's really an honor for me to introduce my colleague, Alessandro Chiuso, from the University of Padua. Alessandro is a full professor at the University of Padua. He had a number of important visiting positions in different universities, and he had many roles as associate editor, senior editor of our major journals and major control journals, and he's also IEEE fellow. And I don't want to use any other portion of the time that Alessandro has to give us what will be surely a very nice semi-plenary talk. Thank you, Alessandro. The floor is yours.
Thank you. So thank you, Antonella. Big thanks to the organizer for inviting me here. Big thanks to all of you to participate in this and attend this talk. I hope I'll not disappoint you. I'm excited to be here 24 years after I was sitting next door as a postdoc in the math department here. And also a big thank to my colleagues, Valentina Breschi, Marco Fabris, and Simone Formentin. And most of the work I'll be talking about today is work I've done with them. And thank to Florian Dorfler and Kid Moffat, with whom I did some work in the past year while I was spending some time during my sabbatical at ETH. So what is this talk going to be about? I should have had another word at the beginning, so predictive. So the talk is about data-driven predictive control for linear time invariant systems. So sorry, I will disappoint Mike Jordan. I'm still here in the linear time invariant comfort zone. And just as a disclaimer, I will not talk about anything related to the IQ approach where you have states and so on. I will not be talking about iterative learning and other data-driven techniques. So if you are interested in that, that's not the right place. So as I said, it's going to be an LTI talk. Of course, you may argue that you can be linear and time invariant, local in time, in space, and therefore you can extend a certain argument to go for deal with time invariant system and therefore go adaptive. Some of the things I'll be talking about at the end are actually meant to prepare the stage for that. And we can go to nonlinear by lifting, using basis functions, coupon operator type of things. But again, this is not the subject of the talk today. The talk will be, by and large, actually completely related to methodology. But of course, we're interested in applications where model predictive control, in particular data-driven techniques, are foreseen to be useful. One of these areas is artificial pancreas, where you want to control the blood glucose within certain thresholds, which are dangerous. Well, if you go outside, these thresholds are dangerous. And indeed, linear model predictive control has proven useful for a number of reasons, among which the fact that you need to account for constraints, both in the output as well as in the input. For instance, you can only inject insulin, you cannot take it out. However, there are a number of open challenges related to the fact that it's hard to have models. Every patient is different from the other. The patient changes over time, and so on. So working with data is a must. Another area of application that I'm starting working with Florian and Keith at ETH is power systems, where as the amount of renewable sources increases, the amount of rotating machines having inertia is decreasing. And inertia is something that brings stability to the grid. And you want to basically control inverters in a way that you provide virtual inertia. And you want to do that without violating constraints. For instance, constraint current provided by the inverter. So you have a dynamical systems, the network, the loads, and so on and so forth. And you want to build a controller. And again here, model predictive control is a setup that handles all these ingredients. However, also here, having models hard and dealing with data is something that is to be looked for. So with this sort of introduction, I must say I got interested into data-driven control quite recently, like 4 years back perhaps, and I must confess I felt a bit lost at the beginning. Well, one might say that you have to control a plant. Well, you don't know the plant. You do system identification. Then you do, design your model predictive controller, possibly taking account into uncertainty, dealing with using robust control techniques and so on, wherever uncertainty might not be matched with the way that you describe uncertainty in robust control, and so on and so forth. So I'll come back to this later on. And one particular and important step in this framework was so-called subspace predictive control, where in a way the model is hidden within the algorithm that goes from data to control design. Then, and this was late 90s. Then 20 years after, people have started working with, let's say, behavioral techniques to describe feasible trajectories, and I'll come back to this later on. But this has a deterministic flavor, and you have to go for relaxed optimization problems in order to account for these non-idealities, and introduce regularization and so on, and I'll come back to this. Another issue that has been debated quite a bit is whether one should actually go with a model and then do something with the model for control, or follow a model-free approach. My take and my feeling is that this is being quietly overemphasized, and one should really think of whether the approach is direct versus or indirect. And again, I'll come back to this. So you should go home today with the following message. So we provide, hopefully, a framework for direct data-driven control, from data to control, which is tuning free. There's no knobs you have to work with. We can work in open loop and closed loop, so we can basically control a plant as you gather data in closed loop. And we can provide stability guarantees, and this is something that is ongoing work actually, and it's not going to be in my talk today. As we go, we will actually talk about models and uncertainty, and show that indeed the model, or one way of describing the model, and its uncertainty are, let me say in a loose way, sufficient statistics for control. And this will provide a sort of separation principle for data-driven control in a linear time invariant setting. So the presentation will be divided in 3 big chapters. And the first one is how do we go and why do we need to go from models to using data? And I'll try to follow some historical developments to explain this. So in a predictive control setting, you're interested basically in predicting how your system will behave, so how your YF trajectory in the finite horizon in the future will be, given certain initial conditions that are given by past trajectory over a certain finite horizon. So this what is called initial conditions Z ini in the right top part of the slide, given a certain control trajectory UF. This goes inside the cost function. You want to optimize the cost function. However, if you don't have a model, you don't know how the system will behave, and you don't know the output, and you want to ask data that are possibly collected in closed loop, what will be the future output if you apply this particular input. So I will start from what was called this behavioral framework for describing the future output. So let's say you want to characterize whether YF will be a feasible trajectory for your output. So let me introduce this name Z for the joint couple of variables, U the inputs, Y the output. You collect in one vector all your past conditions, so Z ini, the initial condition for your control, UF, the control signal, and YF, which is your predicted future trajectory. You ask whether this is a feasible trajectory for your system. So find data-driven conditions to describe this Z. Well, people have been using what is called this fundamental lemma, popularized back at the beginning of 2000 in this work by Jan Willems and co-workers, but that relies on, I would say, older ideas that were popular in the 80s, on subspace identification. And basically what it says is that you take your data, you fill a Hankel matrix, call it H, and if trajectory is feasible, given a certain Hankel matrix with your data, if it lies in the image of the Hankel matrix, or equivalently, if it stays in the kernel of the Hankel, if there is a vector phi that is in the kernel of the Hankel matrix that annihilates your vector. So you have an image representation, you have a kernel representation. A kernel representation you can think of as a model. So phi transpose would be, the vector phi would be your model. But in a deterministic setting, one description and the other are completely equivalent. So talking about a model-based or talking about data-driven is really a matter of how you call things. It's actually the same object. However, deterministic thinking, so saying that your future trajectory will be exactly described by the image of the Hankel matrix is not realistic. And therefore, people have formulated optimization problem by adding slack variables, relaxations, regularization. And one way to do so was this by now famous deep C algorithm introduced by Jeremy, John, and Florian a few years back at ECC, actually, if I'm not mistaken, where basically you optimize a cost function. J is what I called L before. Sorry for changing your tracking plus control cost. And you add some regularization terms that penalize the variables that help you to describe the trajectory. And well, you end up with two regularization parameters. There are different ways of framing the problem in this form. I chose just one. So I don't want to be general here. I don't care. I actually particularly like one of the work there, this distributionally robust formulation, which actually shows that it's natural to introduce this L1 regularization from a distributionally robust perspective. But the point is, tuning these regularization parameters in practice is something that is really critical. And a performance in closed loop, what you see there, can be arbitrarily good or bad depending on how you choose them. So you have to choose this regularization parameter. So let's try to see. The point is, this is critical. And to do that, you need to perform closed loop experiments on your true system or with a simulator, and actually also with the same reference signal you want to track. So for instance, let's say you want to track this reference signal over that horizon. And let's say that I don't tell you what the system is. I don't care. So you use your favorite, well, not your favorite, a model predictive controller that knows exactly your model, and you get the performance over a number of Monte Carlo experiments that are on the right, on the left-hand side, MPC. You run deep C, you tune your hyperparameter by performing closed-loop experiment with that reference signal, and you get that performance, which is pretty good. Then you say, okay, basically, you did not have access to the right reference. Somebody told you to tune hyperparameters by performing closed-loop experiment with a different reference signal, the square wave that you see there. And then you close the loop and try to track the other one, the first on the left. And you see that performance degrades quite significantly. As a small spoiler, what you will see in the presentation will not require any tuning, so you really don't care, and performance will be better regardless. This tuning is actually pretty computationally intensive. I will not comment on this. And well, you may argue there are heuristics for tuning these parameters, but this is not the subject of the talk. So let's try to go now beyond the deterministic thinking. Let's see whether this helps to formulate this regularization problem in a more principled way. And we ask help to work that Jan Willems did right before passing away in 2013, trying to extend the idea of behaviors to a stochastic setting. He did that in a completely static scenario. But basically, the idea was that you want to replace deterministic relation between variables, that is the black line, with uncertainties on the relation by basically describing sets where your pair, in this case current and voltage, should stay. And you can give probabilistic descriptions, sorry about that, probabilistic descriptions of this set, this uncertainty. So long story short, this is equivalent of to going from a deterministic kernel representations, phi transpose z equal to 0, for where z is your trajectory, to a stochastic representation where you allow that phi transpose z is a random variable with a certain probabilistic description. Well, if I take this z and I just reorganize variable and take just pull out y at time t, so the last one, and I just take z ini, which is the remainder, and just rename variables, you can write the same equation as a predictor equation. So y is equal to phi transpose z times z plus some uncertainty. So that's my, and this serves for the next steps. I would like to thank Alberto Padoan actually for many discussions last year when I was ETH on this behavioral stochastic type of extensions. So take home number one. We should go from a deterministic representation or a behavior, if you want, to a stochastic representation. And we can think of this stochastic behavioral representation, which, there are technicalities to go to from the static to dynamic case, but let me sweep that under the rug. They can be think of models for a predictor. And if we call y hat your predictor, y hat will be a linear function of your past data. We're talking about linear behavior. Linearity assumption is always there here. And rho, this parameter, the length of this vector phi or the length of z is a complexity measure that describes your model or your trajectories. So now we have the second part. How do we use this sort of formulation to get to a separation principle for data-driven control? And the key point, which is obvious, I would say, certainty equivalence does not hold. You cannot just take your model and plug it in and do control, estimated model, I mean. So which are our working assumptions? Again, we have a prediction equation for your system, for your data, let's say, and we basically allow for the complexity to go to infinity. So this the length rho, in principle, can be anything. So we include all possible predictors, just asking that these predictors are, to some extent, decaying over time in terms of their memory. So you forget the far past. So basically, let me go back. These are infinite order ARX representation, and any pair of stationary signals under minor technical assumption can be represented by an infinite order ARX. Under linearity assumption, of course. So your model class is all possible linear time invariant systems. However, you have finite data to work with, and there's no way you can come up with an infinite dimensional model. You can think of this as a non-parametric representation of your predictor. And indeed, as Håkan Hjalmarsson pointed out quite some time ago, you need to consider, and actually you need to be happy to work with near optimal, what he called near optimal restricted complexity model to do control in our case. So basically, what you end up with is truncating this infinite order autoregression to a finite order. And of course, you may say, okay, this is a model order choice. Well, if you assume that this is decaying over time, at some point, the relevance of whatever is in the far past is so little that from finite data, you can never distinguish its contribution. And indeed, you can also make this difference, and you can bound this difference. Things can be done quite rigorously. And again, I will not enter into that. And actually, Akaike, some 40, 50 years back, told us how to do this with a prediction frame, with a prediction point of view, by introducing what was called the final prediction error criteria, so that you truncate at some point, because estimating over that threshold doesn't really mean anything and doesn't help at all. Actually, it makes your life worse. However, our focus here is not on control, on prediction, but it's on control. So we want to. So the wording is fitting the model is only half of the story, and again, certainty equivalence will not and does not hold. So the question is, how is the uncertainty that we have will impact the control and the control cost? So let's go back to the objective, which is estimating, well, which is computing the control cost you want to optimize. And then you have data. Your data gives you information on YF, that is your prediction, and therefore on the control, on the cost function. So in principle, you could compute the probability distribution function of your control cost as a function of your data, so the conditional distribution. And this is what you need to basically have to compute, to retain from your data, to compute the optimal controller. So I would call it a sufficient statistic for control, the distribution, okay, which is an infinite dimensional object, and I'll come back to that later on. But before going to addressing this infinite dimensional issue, let me say, how do we optimize the conditional distribution? What does that mean? So just pictorially, you have cost on the horizontal axis that depends on the control that you choose, and on the vertical axis, the probability that cost is realized conditionally on the data that you have seen. And you want to optimize the shape of that function as a function of u. So we need to attach a risk measure that tells you how much you like a certain probability distribution, posterior probability distribution of the cost. So what we define here, final control error, in a way to mimic what was called the final prediction error by Akaike, is a risk functional of the conditional distribution of the cost. And then you want to optimize this risk functional. So let's try to be a bit more concrete, and let's make one example. So one way to introduce a risk functional on probability distribution is to consider this what is called the conditional value at risk. So basically, you don't want the cost to be large. So the conditional value at risk says choose a value alpha, which is a probability level, and the conditional value at risk of level alpha is the average of the cost, conditionally on your data, of course, but under the condition that you exceed a certain percentile of the distribution. So it's the one indicated by the red arrow. And then you can minimize that as a function of the control. So you want to keep it that small. Of course, conditional value at risk is quite hard to deal with, but there is a special case which is rather easy to handle, which is the case in which you take alpha equal to 1. So alpha equal to 1, alpha is the probability of exceeding the threshold. So if you take the alpha equal to 1, the threshold is equal to 0, conditioning goes away, and you're left with the conditional expectation. So for the moment, let's deal with that, because this is something we can compute. So can we actually compute? The answer is yes, we can. And indeed, there are two steps which I'll not basically discuss. I'll sweep under the rug. So we need to introduce a prior on models, these infinite order autoregressions. If you do have a prior, just keep it. It will be useful. If you don't, who cares? You take the non-informative prior limit, again, technicalities, and work with the non-informative prior limit of this conditional expectation. So, and this is what paves the way for a direct data-driven control design. So if we can compute the expected value of the cost given data, and we can optimize, we're targeting the control objective. So this is a direct method. And we will see that indeed this conditional expectation can be written as the sum of two objects, J and R. And J will depend on the predictor, and R basically will depend on the uncertainty. And therefore, predictor and uncertainty will separate data from control. In this sense, there's a separation principle. So how does this go? Just to be a bit more detailed. So this decomposition is nothing but the decomposition of the expected value of the square of a random variable into the square of the expected value plus the variance term. So nothing deep in it. The first term, after a bit of math, turns out to be a certainty equivalent cost, with plugging in the predictor that you estimated using your infinite dimensional or truncated model. Whereas the second term, you can think of it as an excess cost that you have to pay due to the uncertainty that you have. But it's a cost that you have to pay just related to the uncertainty on the controller, on the predictor, but also on the effect that this has on your control objective. And it turns out that, of course, in this linear quadratic scenario, it will be a quadratic regularization with suitable sigma, u star, and so on. You can compute all of them from data. That's the point. So all those quantities that you have on the board are computed from data. And if you want a pictorial sort of representation, the excess cost that you pay for due to uncertainty is basically mapping the variance of the predictor, the uncertainty of the predictor, into a function, a quadratic function that tells you in which direction you have to more risk acting on a certain control, in which direction you can be more sure about it. So to be even more concrete, how do we actually compute this thing? Well, if you take the non-informative prior case, basically you boil down to least squares. So if phi is a vector of coefficients of this A or X model, then I just take least squares to estimate phi and to estimate its variance. These quantities are just based on inner product of Hankel matrices that you build with data that are nothing but cross covariances between your data. And these are sufficient statistics for control, because once you have computed these two quantities, sigma hat yz and sigma zz, you can just plug them in the expression that we had before, compute J, compute R, and you have your cost that you can optimize. So let's go back to the example that we had before. We had seen that tuning was sort of an issue, and indeed, actually, I swept under the rug a few outliers that were not there. So let's see how things go on the outliers. So if you take 5% of the worst closed-loop experiments, you get this performance. So again, the outliers are critical in terms of hyperparameter tuning. Of course, it's just an example. It's just showcasing what this was not built on purpose. Just the first example that you take from a MATLAB simulation. So whereas optimizing the cost that you just seen in the previous slide, you get what you see on the right. So even the outliers, let's say, the worst performing trajectory, are pretty close to your target. So to wrap up, this final control error provides a way to optimally regularize without tuning. And the optimal regularization accounts for the uncertainty that you have in prediction and its effect on the output to the purpose of controlling your system. And regularization depends on the reference signal and on the given experimental conditions. So if you change the reference signal, just change the regularization, because that's the way it goes. So last part will be about how do we go from a linear time invariant to at least drop the time invariant assumption, and hopefully be able to adapt as time goes to hopefully slowly changing variation. So what do you need to do this? Well, first of all, if things are changing, you don't want to look at data far back in the past. So you want to keep this row, that is the number of data that you look back in the past to predict, small, possibly violating what a Kaike will suggest you as a truncation rule. And also you want to be able to use data gathering closed loop, because if you want to adapt as you control your system, your data will be affected by closed loop issues. And therefore, you need basically to be able to keep the size of your Hankel matrices small and avoid closed loop bias. Sorry, I was too fast. Okay? So I'll first talk about the first point. So keeping rows small. And basically, the second part will be just a bonus that we get. So the issue, which is well known, of course, if you build a time invariant predictor based on the entire path of your signal, and you just propagate it forward in time using stationarity, well, it's a steady state predictor. Wherever sorry. What happens if instead you violate this assumption that the length of your path horizon is enough? So let's take rho small and try to challenge the assumption. Well, in theory, we know that, you can compare the predictor that you'd get from using a very small rho. And the predictor, I mean the predictor over the entire control horizon, so capital T steps ahead, and compare that with the one that you would get if you were using let's say, a right rho on a long enough rho. And we know that as rho goes down, becomes small, indeed the difference between the two predictors is pretty big. And is this going to affect closed loop performance? Indeed it does, because if you attempt to track a square wave with a simple double integrator and you have data collected in closed loop, doesn't work, doesn't track anything, as you take rho very small. Here we changed it a lot. The rho was equal to 1, so the smallest that you could possibly take. And this is not just one experiment. If you do Monte Carlo, I mean, they're all bad. Okay? So let's see if we can fix this. As control people, and it's not something I should teach you, we're very aware that transients are important. And indeed, in a model-based scenario, you come to me and say, hey, if you have the model, you run the Kalman filter, you know how to do a time variant predictor by implementing the Riccati equation, the transient Riccati equation, and using every time the right Kalman gain, let's say, right? So from a pictorial point of view, you have on the vertical axis time, let's say that you have rho that is small, so you have data in a certain horizon, you want to do one-step prediction. Then once you do a one-step prediction, basically you're adding one data point, and you want to go one step more, one step more, and one step more until you reach the control horizon. And all these predictors are working in a time-varying setting because they're using a short leading data, short past. So they'll all be different, basically. So without asking you to follow the details, the question is, can we account for this in a data-driven setting? And the answer is yes. So just to summarize, if you had the model, a state space model, you would run a Kalman filter to build this transient predictor, and then with the transient predictor, you run your MPC, and you don't care about how long rho is. We can do actually exactly the same computations that we did for the, let's say, steady state case, also in this time variant scenario, and come up with a decomposition of the control cost, the final control error, as the sum of two objects, providing again a separation principle for that. Is it hard? Well, again, you're not supposed to read. It's very simple. Just take your data, organize the data in a Hankel matrix that is suitably ordered, and let me just say that. You perform an IQ decomposition, you play a bit with the L factor, and you get your transient predictor. That is this phi hat matrix that using condition, and control tells you what your future output will be. And then using this machinery, you end up with a decomposition of the cost again as a certainty equivalence part plus a regularization or excess cost, if you like. That accounts for the uncertainty. So is this going to work? Well, I'll let you judge. The red line was this, let me call it fixed length predictor that was based on the assumption that rho is big. And the other one is the transient, the one that I just attempted to describe, and I surely don't mean you follow all the details. But the blue line is tracking pretty well, regardless of challenging the assumption on rho. So bottom line, this truncation that at the beginning we started with is not really a critical issue. And again, are these two trajectories, special trajectories that I've chosen? Not at all, because if you look at the box plot of a number of Monte Carlo simulations, the one that you see on the right-hand side is this transient construction. That does a pretty good job as compared to, let's look at the exploded view with respect to a PD controller, for instance. Okay. So last, I'm getting to the end, that we get as a bonus. What about closed loop? Well, for those of you who are not familiar with this issue, it's a pretty simple thing. In closed loop, so if you have a control system and you have noises that affect the output, noises will be fed back by the controller to the control input. So future inputs will depend on past noises. Okay, and this is shown in the picture on the right-hand side, showing correlation between inputs that are on rows and the future noises that are on columns. Is this bad? Well, this is not bad in principle, and this is fact that was well known back in the, let's say, 90s in the identification literature on subspace identification, for instance, where these issues came. And is this bad? Well, it's not bad in principle. It's just bad depending on the way you just extract information from your data. And this deterministic behavioral thinking actually is not accounting, is not properly modeling the effect of noise, and is not properly accounting for this. So it will basically fail. So is it true that they fail? Well, let's take again the same example. You're controlling a double integrator to track this square wave with feedback. Very small noise, just to make things work. And you see those overshoot that are provided by this deep C that is based on this behavioral approach. And the question is this related to tuning? Is it related to bias? Well, if you know the system, you know your data, you can actually compute the effect of the bias on the controller. And indeed, the picture on your right-hand side shows that. So the dashed line is what your model will think that you will do with the control. So you perfectly track your reference signal, the dashed line. And the solid line is what your controller, when you close the loop, actually does. So it overshoots. And the difference between the two is actually accounted for if you look at the dotted line. That's the computed bias in prediction. Knowing the model, knowing everything. And if you subtract the realized trajectory from the computed bias, you indeed get the predicted trajectory. So that difference is indeed due to the bias issue in handling your closed loop data. And I said I was not using much noise. If you add more noise, the whole thing goes belly up in closed loop. Whereas the algorithm in blue that I just described, that is based on this one-step prediction sort of model, does not at all have these issues about closed loop correlation between future inputs and data. And this is, I mean, possibly a well-known thing, but putting all things together is... So, to conclude from this last chapter, this transient predictor framework allows to deal with short data segments. And contrary to all these deterministically, let's say, inspired data-driven predictive control schemes, it can handle without any issue closed-loop data. You may argue that there are extensions of, let's say, model subspace predictive control to deal with closed-loop data. So this is not entirely new at all. So to conclude now the talk, we have provided a separation principle that in a way answer to the question, do we model or do we not model? Well, the model and its uncertainty are sufficient statistics. So in a way or another, you need to come up with something to call it a model, call it covariance matrices, and you just don't call them model, fine. But that's the model hidden in between. But you need to account for the uncertainty, as Mike Jordan was pointing out this morning very many times. We have a closed form expression for regularization that it says how do uncertainty affect your performance in control and where should you be more cautious. It depends on reference and excitation and does not require tuning. And again, if handled correctly, you can deal with short data segments and there are no problem in closed loop, which are two key ingredients, or three key ingredients actually. Short data segments, closed loop operation, and no tuning required, that are opening the possibility to go for adaptive online. That is indeed one of our next or ongoing things. All these algorithms are based on basically IQ decomposition or Cholesky decomposition, of which you can give in recursive implementation, which are efficient. The excess cost, which, or call it regularization, is actually something that tells you where do you have more uncertainty and where does your uncertainty affect your control. And you can exploit that to decide how you need to control your system to avoid that this uncertainty or the effect of uncertainty on control actions increases. So you have a way to handle to deal with the exploration-exploitation trade-off. We're working on stability issues of these algorithms, and of course, as I mentioned, applications in power systems and artificial pancreas. And I think with this I conclude, and I thank you all. Tack så mycket.
Thank you very much, Alessandro. Thank you also for the perfect timing. It was really ideal. And so I open the discussion. If you have some questions, I think that we have time for 1 or 2 questions. I saw some hands raised.
There is one over there.
Probably you need a microphone.
Wait for the
moment.
mic.
Wait a moment that the microphone is arriving.
Thank you for the presentation. Maybe a simple question. Why not just do the system identification first and the model-based control instead of the method you suggest? What is the advantage of taking the uncertainty into account if you have linear time invariant systems?
Well, basically, let me go back to one of the last slides, if I can. Oh, there is something. Okay. So the function that you want to optimize needs to account for the uncertainty, because the regularization term that you have is capturing the effect of uncertainty on your control cost, on your expected control cost. That is the most you can do, the most you can have in terms of.
Linear invariant system, you will get the exact model, right?
If you have enough data,
I'm
running away of the say deterministic framework in which your data tells you exactly what the model is. Then I'm back in a model-based control design, and it's not very interesting as a question. Because not your question. I mean, it's not interesting the setup. So you want to sit in the middle where your uncertainty is something that you actually need to account for.
Because I assume that this row, the small row, because you cannot go with one, we see that it doesn't work. So there is some small enough row you need for a good system model. Maybe that is also true for a correct system identification. So that was the question.
There are 2 questions. There are 2 things that you mentioned. So one is row, which is the amount of data in the past that you used to build your predictor. So even if you had the perfect model, you could compute a one-step predictor based on just one data set. Then you give me 2 data sets, well, the one-step predictor will change, and so on. And this would be a perfect prediction with the information available. Another thing is how much data, so calligraphic D, do you have to give you information about the model, which is another thing. So rho is not the amount of data that you have, it's the amount of data in the, say, closed loop in the past that you use to perform your predictions. Okay.
Okay, let me see, maybe another short question, if there. If not, maybe we can conclude here. And I don't see any other questions, so just give a second round of applause